Hello everyone, today we're talking about what are called abstract vector spaces and subspaces. This is material from 4.1. So we're going to be changing gears today, kind of talking about something, well, more abstract than usual. But let me just set the stage a little bit. So this is going to be inspired by things we have studied. So what have we kind of worked with so far? We have been working with what we called vectors, right, in Rn, right? So we were calling this Rn. So this, for instance, if I had 1, 0, 2, this is a vector in R3, right? And, we were working with these in various contexts, but if you remember the sort of two defining properties that these guys have, that I've been trying to stress throughout the course, is that these objects can be, right, there's two things you can do. You can add them, so objects can be added. For instance, I can take 1, 0, 2 plus, 4 minus 1, 0. Right, I'll let you figure out what that is. And they can also be scaled. I can take, 5 times 1, 0, 2, and that gives me something. So, the addition of two vectors and scaling a vector by any real number is possible, and it gives you a new vector. So it turns out these operations of addition and scaling can make sense in the context of other objects, let's say. So we'll see in a second some examples, but for now I'll be a little bit vague, but it turns out this shows up, for instance, in physics for sure, engineering, maybe more recently, machine learning. But, whenever you have kind of a world of things where you can add and you can scale, it's going to be somehow in this context, and it'll fit into this world of linear algebra. So let me actually make a definition now. So, abstract vector space. I'm going to define what a vector space is. So let's call it V. So this is going to be a non-empty collection of things, let's call them, of objects that we call vectors. Okay, so these are abstract objects. We're going to call them vectors, right? They're not necessarily these lists of numbers. But then you give me the things, and then you also tell me how to add and scale. So together with two operations, let's call them addition and scaling. So in other words, if U and V are in this vector space V, then U plus V is defined somehow. And then, of course, the other thing is scaling. If U is in V and C is a real number, then C times V is defined. So these both have some rule that defines them. And I'll show you an example in a second. Now, of course, it can't just be any old kind of rule that you just randomly write down. These operations must satisfy some properties. So these operations must satisfy a list of what are called axioms. Axioms is just another way to say rules. And there's 10 of them, so it's a little bit complicated. I'm not going to write them down here. I actually this is a scan from your book, so this is from chapter 4.1. This is the list of all the properties. I don't expect you to memorize these, but so there's 10 rules here. For instance, the second rule says that if I take U plus V, this should always be V plus U, no matter what you take. So this is for any U, V in your world. But I want to emphasize 4. So number 4 is an important one. And what this says is that there exists what's called zero vector, which we'll usually call 0, right, with the property right, what does the 0 vector do? Well, whenever I take the 0 vector plus something, any vector, I get that vector back. And of course, that should also happen if I add on the other side, right? I know that addition is commutative, and this should happen for any v in v, okay? So again, I want to emphasize that part of the data of a vector space, when you tell me that this thing's a vector space, I need to tell you not only how to define addition and how to scale, I need to tell you what is that 0 vector. Okay, and again, we'll do an example in a second. Let me just say, see book for the complete list. There's going to be something about distributive law there. There's going to be, well, various things. I'll let you look that up. But let's do some examples. So, of course, the go-to example is going to be Rn itself, right? So Rn is a vector space. Remember, Rn is just all vectors of the form, x1 through xn. So I have lists of numbers, n of them. This is a vector space with the usual, we already talked about this, the usual vector addition and scaling. And again, I have to tell you what the 0 vector is. The 0 vector is going to be what you think it is. It's going to be the thing that has 0, in each entry. There's going to be n of them because we're in Rn, right? So remember, I tell you I'm in R5, so the 0 vector will have five zeros in a column. Okay, let me give an example that's different, that's new to us. So Pn is going to be the set of all polynomials of degree at most n, and so I should say with real number coefficients. Okay, and so this is, what is my vector addition going to be? Well, it's going to be the usual, again, addition, right? If you have two polynomials, you can always add them. And scaling, you can also scale a polynomial, and I'll show you an example in a second. And what's the 0 vector here? The 0 vector is going to be, well, it's going to be a polynomial that doesn't do anything when I add it to a new polynomial. So it's going to be 0 plus 0t plus 0t squared plus 0t to the n. So this is a polynomial. I should say that my t, right, a polynomial always has this unknown, this variable. I'm going to call it t here. So if I'm in degree at most n, I want to take the polynomial that has zeros everywhere. So let me show you a concrete example of this. Let me pick one of these Pn. So if n equals 3, let's look at P3. This is polynomials of degree at most 3. So what are some things in here? Well, I can take v, let's say, is root 2 plus t squared minus 4t cubed, and then w can be, 5 plus, let's say, 1/2 t minus 3t squared, or something like that, right? So I'm allowed, t is my variable. Remember, a polynomial is just constant plus something t squared plus etc. I can use anything for my coefficients, any real number. And notice you can add, right? v plus w is going to be, I just add the two things. So my constant term is root 2 plus 5. My t stuff is 1/2. My t squared looks like minus t squared, right? And then I've got a t cubed stuff. Okay, I'm just adding those two as you would. And then, I can also scale. So I could take like 4 times v. That'll be 4 root 2 plus 4t squared minus 16t cubed. Okay, so that's what I mean by vector addition, vector scaling. And then the 0 vector, of course, was, well, in this case, we're degree 3, or at most 3. So I take a polynomial that has, well, it's kind of a silly thing, but it's a polynomial that has 0 as every coefficient. Now, let me just note something. Why do we have polynomials of degree at most 3? So notice if I took u to be, let's say, 3 plus t, let's say, plus 4t cubed, then what do I get when I take u plus v? So taking that same v here, and I add these two now. Well, the constant term is 3 plus root 2. Then I get a t plus a t squared. But notice now that the t cubes, the minus 4t cubed and the plus 4t cubed, cancel. And so this is now a degree 2 polynomial. But that's okay, because I said polynomials of degree at most 3. But if I had insisted on polynomials of degree equal to 3, I'd be in trouble, because it's possible to add 2 polynomials that are degree 3 and leave that world. And so I don't want that to happen. I want to stay in the world of, wherever I live, and so that's why we do degree at most 3. Okay? Let's see. So maybe I'll do one more example. We're going to use this later. So let me call this M2. This will be 2 by 2 matrices with real number entries. So things that look like this, right? Notice that I can, what's the addition going to be? It's going to be, coordinate-wise addition. So this will be maybe what you think it is. And what's scaling? So if I take lambda times an A, B, C, D, this would be also coordinate-wise, lambda A, lambda B, lambda C, lambda D. So this would be what I would call coordinate-wise vector addition and scaling. The 0 vector here is, well, what's the 2 by 2 matrix that doesn't do anything when I add? It's going to be this thing. Okay, so you can check that those these rules satisfy the axioms that I, didn't tell you everything about, but gave you some hint of above. Okay, so I think I'm going to end it there with just one comment. So maybe I'll just say next time we will talk about subspaces of vector spaces. And in a picture, what this is going to happen, so here's my cartoon here, is that if V is a vector space, so it's the world that we live in, we're going to look at, sub-objects in there. So, these are my polynomials of degree at most 3, and I'm going to look at a certain sub-collection of those things. So this will be a subset of the satisfying some, again, axioms or properties that make H itself a vector space. Okay, so I think I'll end it there, and we'll continue next time.